Bayes nets are very, very general. A lot of things that we've done or are going to do actually are special cases of Bayes nets. So naive Bayes, if you remember naive Bayes, the assumption of every two predictors are independent of each other given the label, is effectively a specific kind of Bayes net. Can you think what kind? Did I draw that for you? I don't think I did. If you have the label here, namely the category that you're trying to predict, and you have all the predictors, all the attributes here, attribute 1, attribute 2, attribute 3, attribute 4, attribute n. These are all nodes. This is a Bayes net that effectively captures naive Bayes. Every node is independent of all of its non-descendants, conditioned on its immediate predecessors. Well, the immediate predecessor of one of these attributes is the label, and all the other non-descendants are its sibling attributes. So every node is independent, condition independent of all the other attributes, conditioned on the label, which is exactly the naive Bayes assumption. We're going to talk about hidden Markov models. I'll spoil the surprise and tell you hidden Markov models are a special case of Bayes net. What are the things you might want to do with the Bayes net? Same thing we do with decision trees and neural networks. First, there's a question of how you construct them, and then there's a question of how you use them, right? Statisticians call it fitting, what we call learning in machine learning. Statisticians call fitting because if you pose a statistical model, it boils down to deciding on the value of the parameters. So fitting the parameters to the data is learning the parameters from the data. It's the same thing. And then using the model to make predictions, statisticians call inference, drawing inferences from the model. So in machine learning in general, you hear about the problem of learning and the problem of generalizing or decision making or classifying or using your model. Statisticians talk about fitting and inference. Fitting is specifically learning the parameters, but there's another kind of learning, and that is learning the structure. I mentioned to you one of the nice things about Bayes net is that you can decide, using your knowledge of the domain, what the structure should be. And sometimes it's a blessing. Sometimes you really want that power. But there are times when you don't know what should be independent of what. And if you're lucky enough to have enough data, you may want your data to tell you what should be independent or not. So there's a whole branch of Bayes nets that deals with how to learn the structure. And that's very, very hard. There aren't very many good positive results, mathematical results. Question, comment?
So in that case you would have no hard bias?
Well, if you allow yourself a priori any structure, then you have no hard bias. But typically that won't be the case. You may allow yourself some limitations on the structure and still try to learn within that context. But even in the extreme case where you allow yourself any structure, then you're right, you don't have a hard bias, but typically what you would have is a soft bias. What you would do then is you define a prior over all possible structures. By structure I mean the topology of the net. Okay, what's connected to what? You will define some prior over that structure such that maybe nets with fewer edges are preferred, are a priori preferred. But the reason it's hard is because Bayes nets are extremely powerful. It's such a rich family. Both the choice of the structure and then the choice of the parameters within the structure is so rich that it's so expressive that you can describe just about anything, and therefore you need a lot of data to be able to constrain it. So there's no free lunch, right? You either make assumptions or you need tons of data. So I'll tell you briefly about the state of the art in algorithms for Bayes net learning of structure, learning of parameters, and inference. You should know that this is it is the most active area of research in machine learning today. Bayes nets also go by the name of graphical models. In fact, we teach a whole course here just on graphical models. I talked to you here just about the directed kind of graphs. There are also undirected graphs that capture typically not so much causality but correlations, not when you're trying to maybe predict. Well, you could use it for both, but the algorithms and the mathematical difficulties are somewhat different between directed graphs and undirected graphs, and the solutions are somewhat different. But they have some overlap as well. So it's a huge area. There are 2 new books that just are coming out this year, this thick, just about graphical models. One of the reasons is that they seem to capture a lot of the other models in them. So let me tell you briefly about first learning in Bayes nets. So as I mentioned, there are several variants of learning. There's learning of the structure or learning of the parameters only. Trying to learn a network structure, if it's not known, if it's not assumed, is very, very hard. There are no results that say that you can do it even if you have enough data, as long as if you have infinite data, yes, but any reasonable amount of data. There are always heuristics and always assumptions. It's a very, very, let's say even, I don't know if you should call it ill-defined task, but it's a very difficult task. Let me just leave it at that. A much more concrete and doable task is if the structure is given and you want to learn the parameters, namely the conditional probability tables that sit at every node. Remember that these tables are either literally tables, if you talk about discrete variables, or they are some families of functions like Gaussians or something else, in which case you need to learn the basic parameters of these functions, like their means and variances. There's nailing down a specific member of the family. Now, even within learning the weights of the parameters, you should break it into 2 cases. What kind of data do you have? If you have, if your data consists of examples of all the variables being known, so think of your data as a table where every row is one input, one example, one training example, and every row consists of the values of all the variables. In our case, 6. I guess there's 6 nodes, so the values of all the 6 nodes. In that case, learning the parameters is straightforward. Why is that? Imagine, it is 6. Imagine these 6 variables you were given many examples of them. So it would consist of, on day 1, storm was 0, and bus tour group was 1, and lightning, storm, bus, lightning, campfire, thunder, and forest fire. Okay, these are 4 variables, content variables, and on day 2 you have some other 0, 0, 1, 1, 0, and so forth, and you have 1,000 of these or more. Now you're trying to learn all of these parameters. Well, to learn the probability of campfire, if there was storm and no bus tour group, all you have to do is go to the storm and bus tour group and look for the pattern 1 and 0. Right? Storm and no bus tour group. Collect all the rows in which this is true and observe in what fraction of them campfire was 1. So you'll simply do the count of campfire equals 1 and bus tour group equals, whenever we say bus tour group should be on or off equals 0, and storm equals 1 divided by the count of bus tour group being 0 and storm equals 1. Right, it's just the relative frequency estimate. It's very, very straightforward relative frequency. It's not guaranteed to give you the correct answer. You now are sophisticated enough to know that this is just a maximum likelihood estimate. And in fact, if these counts are small, it's not a very good estimate, and you may want to smooth it. You may want to add some pseudo counts. So it's not open and shut. I mean, there's still things you need to do and worry about. But at least you have a very clear methodology for how to do it. And you do have the maximum likelihood answer if you want it. The maximum likelihood answer is based on of relative frequencies. A much more interesting and much more difficult situation is when this table is not completely full. Let's say some values are not known. The wardens that work in this park keep track of some of the information, but they may not have all the information. The first thing that may come to your mind is to say, well, let's throw away all the rows that have some missing values. And that's okay to do if it's a small fraction of them. But in problems with hundreds of variables, it is usually the case in real-world problems that all the rows will have some missing values. You can have 100 variables and each row will miss 1 or 2 or 3 or 5 of them. So you can't afford to throw away that information. And neither should you have to. You can still take advantage of that information. So in that case, you have a table that has some unknown values. I don't mean don't care, I just mean unknown. It turns out you can still seek the maximum likelihood solution. You can still ask yourself, for building each one of these tables, which value of the parameters would assign this data the highest likelihood. But it's no longer a straightforward mathematical matter to derive the answer as a relative frequency. In fact, you need to engage in an iterative procedure called EM, which we will talk about later in more detail, which will converge on a local maximum of the likelihood, and in fact you're not guaranteed that it's the global maximum. Yes?
So, for the campfire example that you just gave us, the campfire is only dependent upon those two variables. But what if how do you reconstruct the table where you're with the field forest fire? It's going to show that forest fire is dependent on bus-tour group from relative frequency count, but it's actually dependent on it through the campfire.
You just gave the answer. It is dependent on bus-tour group. It's just dependent on it indirectly. So they're not independent, right?
Right.
This and this is not independent, and it will be reflected in the data. You're correct. Maybe I didn't understand the question.
So the question was, how would you know not to draw a line directly from bus-tour group to forest fire? Okay. So you are dealing with the question of how to decide on the structure of the net. Right? Okay. The last 5 or 10 minutes we were talking strictly on deciding on the parameters. Before that, I did mention that if you wanted to learn the structure, that's a very difficult problem. And what you just said now is one intuitive explanation of why it's difficult. The fact that there's correlation in the data between forest fire and bus-tour group does not mean that they need to be connected. If they're already connected through campfire, what you need to ask yourself, is there excess correlation? Is there excess influence of bus-tour group on forest fire beyond what is mitigated through campfire? So you may want to ask yourself, you can ask the question in information theory terms, is there mutual information between bus-tour group and forest fire conditioned on campfire? Okay, that would be one question to ask. Another question to ask is, if I build a table, ignore these for example, suppose they didn't exist, you're just asking about just campfire or campfire and bus-tour group together going to forest fire. If I built an estimate for forest fire based only on campfire, or I built an estimate based jointly on both of these, would the second one be significantly more accurate? Which is another way of asking the same question, measuring it slightly differently. Does this give you information about this beyond what you already got from here? Right? But that's just the tip of the iceberg. There's actually a lot of intricate implicit dependencies that exist. I mean, there's paths that go from here all the way back to here. And in fact, one could argue that by knowing whether it thundered, you learn something about this, which is sometimes counterintuitive. So there are rules about how to trace dependencies in Bayes nets, and how sometimes having a known variable in the middle allows you to clamp and separate what's on one side of it and the other side. It's called a Bayes blanket, I think is the term for it. So being able to separate part of the network from another part. Okay, so this is learning the network, the structure. Going back to learning the parameters, we said that if some of the values are missing, which is usually the case, we can still seek a maximum likelihood solution, but the algorithm for doing that is more complicated, more computationally intensive, and it's not guaranteed to give us a globally, truly maximum
likelihood solution, more likely to give us a local maximum. What about inference? So by inference, we mean that the structure of the network is known and the parameters, namely the conditional probability distributions of every node conditioned on the parents, are fully known. So you can write down explicitly the form of the joint distribution of all the variables. So if I gave you the value of all the variables, you could tell me what is the probability of that particular configuration. That's wonderful, right? You can tell me that by using that chain rule that I showed you before, just the product of all the conditional probabilities of all the nodes. But now suppose I give you only some of the variables. Let's take the simplest case. Suppose I give you all the variables except one, and I say if bus 2 group is 0 and campfire is 1 and thunder is this and this and that, what is the probability that there was a fire yesterday? So I'm not asking you to bet that there was a fire or that there wasn't, although you could do that. I'm asking you more exactly to give me the probability of that, conditioned on all the other variables being known. That's inference. You could also I can also ask you the probability of fire conditioned on some of the variables being known. So if I have 6 variables, I can give you 3 and ask you for a value of another one, and the other 2 I don't know. So what you will conceptually need to do is average over all possible combinations of the other. So in principle, you could literally add up, since you have the full network, you could add up all possible configurations and answer that question. So the question is answerable in principle. But since you typically have a large number of nodes, a large number of variables, this addition sometimes would involve exponential number of components. So you want to be smart about how you do that. And secondly, if they're not discrete variables, if they're continuous, then it's not addition, it's integration. And that might be hard as well. But this is what's at the heart of inference in Bayes networks. So as I said, the Bayes net contains all the information needed for the inference, if you were just able to do all the computation, because you know the joint probability of any possible combination of events. If only one variable has an unknown value, it's easy to infer. In general, even though the problem is computable, it is NP hard. So the general inference problem in Bayes nets is NP hard. There's been tremendous amount of work on inexact inference, on coming up with approximations to the inference problem under different conditions. So you can imagine sampling of different types, sampling the space of possible configurations, and so forth. Monte Carlo is a particular general method for sampling, for moving sort of randomly in space and to try to get a global answer by sampling. Questions? Okay, let's talk about hidden Markov models. And I'd like to do it with a story. So I'll tell you the story. The story is that you have an office at CMU, and you have some office mates, and you have particularly one office mate who lives in Monroeville and who comes to CMU, commutes by car every day. And they're a little anal, so they like to keep statistics of how long it took them to travel, and they have many different ways. I don't know, those of you who live out east, there are several different ways of coming from Monroeville, but let's assume for now that they always, whenever they can, they go through the Squirrel Hill Tunnel. And the Squirrel Hill Tunnel, as you know, is sometimes congested in the morning. So the amount of time it takes them to get to school varies. They always leave their home exactly at 8 o'clock in the morning. I know that already makes it a very unrealistic story. And they arrive, 15 minutes, 20 minutes, half an hour later. It turns out that how long it takes them to get to their office depends on the state of the tunnel. The tunnel sometimes undergoes construction. So sometimes one lane is closed and there's slower traffic. And other times, maybe more rarely, the tunnel is closed altogether and they have to take a bypass road, maybe through Forest Hills or Wilkinsburg, in which case it tends to take them even longer. So imagine these three conditions, and at any one day, the tunnel is in one of these three conditions, either open or closed, or what I would call semi-closed. Just one lane is open and you have to share it. Open, closed, and semi-open. Because these are three fundamentally different situations, your anal friend keeps separate statistics on these three conditions. So, on days when the tunnel is open, he keeps the statistics of his travel time from home to CMU, and one day it took 12 minutes, another day it took 14 minutes, another one it took 11, and another one it took 18, and another 15. Collects a lot of data like that. In fact, he even draws it in a histogram. So this is travel time in minutes. I'm sorry, this is not travel time. This is travel time in minutes. And the histograms, let's say the earliest, never took him less than 9 minutes. 9, 10, 20, 30, and mostly it took around here. There's someone here. Not surprisingly, it looks a little bit like a Gaussian, which is what you would expect from travel time, because it's a combination of a linear addition of many independent variables, central limit theorem. Now, he also collects the statistics on what happens on days when the tunnel is semi-open. And not surprisingly, it took mostly longer, 15, 19, 23, 26, 18, and so forth. And I'm going to draw the histogram, but I'll draw it on the same picture, so it would look something like this. And on days when the tunnel was closed, now it took 25, 26, 25, 24, 22, 32, and the peak was here. It was like this. So you have three Gaussians with some overlap between them. Now the tunnel is not open and closed capriciously. The majority of the time it's open. Construction happens at specific times, and the thing about construction is it's not a one-day thing. Once construction starts, it's going to stay for a while, right? So in fact, if you knew that the tunnel was closed yesterday, that means it's much more likely that it is closed today than if you knew that yesterday it was open. So we want to capture this dynamic behavior of the state of the tunnel. And we're going to capture it by putting links between these states, much like finite state machines that you probably learned. So if the tunnel was open yesterday, it has a certain probability of being still open today, some probability of being closed, and some probability of being semi-closed. I would say it has a probability of maybe 0.95 of being continuing to be open, and maybe 0.01 of being closed, and 0.04 of being semi-open. Because when you start working on a tunnel, you close one lane, you do all the work you can, then you close both lanes if you have to, and so forth. Whereas if it was closed, it's closed. If it were closed, it's likely to continue to be closed for a while, let's say 0.7. This corresponds to an average job of 3 days maybe. Spend 2 to 3 days here. And then there's some chance that you would move first to semi-close and some chance that you move back to here. The exact numbers are not important. The important thing is, say this is 0.8, 0.1, 0.1. The important thing is that all the errors that come out of a particular state, their probabilities have to sum to 1. Because they describe basically a probability distribution over the state of the tunnel the next day, conditioned on its state today. Now notice that we're not capturing the probability of the state of the tunnel tomorrow conditioned on what happened yesterday or the day before. We're only modeling it based on what happened today. So we're making the assumption that the state of the system at one time depends only on its state at the time step before it. This is called the first order Markov assumption. We could make other assumptions. We could say it depends on the state of the system in the last 2 days. That would be the second order Markov assumption. And there's a third order Markov assumption. And there's also a zero order Markov assumption. The zero order Markov assumption is that the state of the tunnel today does not depend on the state of the tunnel any other time. So it's drawn independently each time. That would correspond to having these 3 circles without the arrows. But maybe with some joint distribution, static distribution that says that 80% of the time the tunnel is closed, 15% it's semi-open, 5% it's closed. By far the most interesting situation is with the first order Markov assumption, because we can capture it, we can work with it. It turns out that even if you believe that a particular phenomenon that you're modeling does not behave this way, but behaves as a second order Markov assumption, you can still take a second order Markov chain and convert it into a first order one. The way you would do it in this case, by the way, is that you would have, instead of 3 nodes, you would have 9 nodes, each capturing the history of the last 2 days. Open, 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 close, open, semi, semi-open, and so forth. So mathematically, you're not giving up much by assuming a first order assumption. You just need to figure out what your states are going to be. What we have here, the combination of these 2 things, is called a Markov chain or a Markov model. The properties of a Markov, in this case the first order Markov model. The property of a Markov model consists of 2 kinds of distributions. The distribution of which state follows which other state, and distribution of, given a state, what tends to happen. What tends to happen is here. So these 3 distributions are called emission distributions, or emission probabilities. The reason they're called emission probabilities is because you think about the state as if the state is emitting that outcome. The tunnel is in a state of being open and it emits the outcome of the trip taking 22 minutes. And you have to realize that even when the state of the tunnel is fully known and fixed, the emission is a random variable. On one day it will be 9 minutes or 12 minutes, and another day it will be 14 minutes. And presumably your anal friend took this data and maybe fitted a Gaussian to it. So they estimated the mean and variance of the Gaussian for each one of these 3 conditions, the white, the orangey, and the green. And they came up with a mean and variance. And then separately, how do they come up with these numbers? How would you come up with these numbers? How would you estimate these probabilities, which by the way are called transition probabilities? So we have 2 sets of probabilities. Transition probabilities governing the move from one state to another, and emission probabilities governing when you're in a given state, what are you going to emit. We said that you would estimate, or your friend rather, estimates these emission probabilities by fitting Gaussians and maybe using maximum likelihood estimate of the Gaussian. How would they decide on these parameters? How would they fit those? Please.
Count transitions and then normalize each one to the total number of outgoing for that node.
relative frequency again. It's a maximum likelihood estimate. So it would be something like number of times in your collected history that the tunnel was open and then the following date was closed, divided by the total number of times it was open. And this would give you the value of going from open to closed. Right? And again, if some of these counts are zero or very close to zero, you might want to do some smoothing, in which case you're not using exactly the maximum likelihood estimate, but a smooth version of it. But it's not difficult to do. We know how to do that. And if you have a lot of data, you don't even need to worry about that. Questions so far? So why would we want to build such a model? Well, if we had such a model, let's first give it names. The transition probabilities are usually called AIJs. It's a matrix, a square matrix of, if you have n states of n by n, and it gives you the probability of transitioning from state I to state j. So if you're in state I, then the next timestamp you'll be in state j. That's AIJ, it's an n by n matrix. What about the emission probabilities? Well, there's one for each state, right? So we would call it B sub j. J varies over the three states here, open, closed, and semi-open. And then it is characterized by another parameter, which is the number of minutes in our case. So B sub j of k would be the probability of travel being k minutes given that we're in state j. So if this is an n by n matrix, this is a set of n probability distributions. Now, it depends on what you're modeling. If you're modeling number of minutes and you're rounding to the nearest whole minutes, then it could be however minutes you think are possible as an answer, 50 or 100 or whatever. If you're actually modeling everything down to a real valued number, you're treating time as continuous, then you can't really count how many answers there are, but if you're modeling with the Gaussian, then there would be two parameters. So this is kind of open, what's here. It's basically the size of your output, size of the space from which your output comes. But there are n of those. And in the transition it's easier, it's n by n. And now, if you look at a particular week and you have a particular sequence of the state of the tunnel and the arrival times, you could calculate the probability of that particular week happening the way it happened. I don't know why you would want to do that, but you could. Now things are going to get a little more interesting. Your NL friend did all this calculation by himself and kept records locked in his drawer. You're not on speaking terms with your NL friend. He's not your friend actually, he's just your office mate. You guys don't talk. And he doesn't share his information with you. So you now need to figure out a way to build this model without the help of your friend. Luckily, since you share the office and since you get up at 7 every morning and you're in the office by 7:15, you are there to record the arrival time. And since your friend is Zainal, you know they leave the house at 8 o'clock every morning. So it's a trivial matter for you to record arrival times and deduce travel times from them. So you have access to the travel times. But what you don't have access to is whether the tunnel was open or closed on that day. And that's a problem. It's actually two problems. One is if you don't know if the tunnel was open or closed, you don't know in which one of these three columns to put that data point. Right? You just get one joint list of arrival times, but you don't know for each one of them if it belongs here, here, or here, or here, here, or here. The second thing you don't know is if you don't know when it was open or closed or semi-open, you can't use this formula how in the world are you going to estimate these transitions? So what for your friend is a Markov chain or a Markov model, for you is a hidden Markov model. What's hidden is the state of the system. What is not a hidden is the arrival times. That's called the observables. So in the hidden Markov model you have these two different creatures. The internal state of the system, which is assumed to be hidden, not observed, and sometimes not even observable in principle. And on the other hand you have some fingerprint, some footprint from the system, which in this case is the arrival times, or travel times, which is observed. It's called observable, and it bears some information, it bears some relevance to the internal states. The relevance is that it tells you something. It's very vague and not clear and not guaranteed, but it tells you something about the internal state. For example, on a day when they arrived in 9 minutes, you can be fairly certain that the tunnel was not closed. On a day that it took them 35 minutes, you can be reasonably sure that the tunnel was not open. Anything in between is sort of a grayscale. Now your job, you have multiple jobs. Two important ones. One is, your family is coming to visit, and they live out east in Harrisburg, and they're driving, and they intend to arrive on a certain day, and you want to know how likely that day the tunnel is to be open or closed, because you need to give them information on which route to take. Or you might even want to know retrospectively, on a given day whether the tunnel was closed or open. Maybe it's a legal case and you're doing forensics. You want to somehow deduce the state of the tunnel from the observation of arrival times. Now you won't be able to deduce it for sure. Even the extreme cases where it took your friend, your so-called friend, 35 minutes to arrive to your office, and you're fairly sure that the tunnel must be closed, but you cannot be 100% sure because these Gaussians really overlap and this goes very far out. So there is a tiny chance that it was open and it's just some other problem. In most cases, the overlap is quite large and you cannot be sure. So if you describe your problem as wanting to know, given a set of observations, what was the state of the tunnel any one day during that observation sequence, you cannot hope to get a definite answer. But we've left the world of definite answers long ago, right? So really what we want is maybe the most likely answer, the most likely state sequence. So I'll give you a week of travel times, and I'd like you to annotate it for me with which do you think is the most likely state of the tunnel at any one time. Now notice something interesting where the first order Markov property comes in. If this was not a first order model, if this was a zero order model, it would be fairly easy to do if you knew the model, because on days when it took 9 minutes, you would say the most likely is that the tunnel is open. On days when it took 35 minutes, you'd say most likely the tunnel is closed. In fact, you would look at these distributions, and you could easily, by me telling you the arrival time of a particular day, you could decide which of these three Gaussian is more likely to have caused it. You may need to use Bayes' formula to factor in that some states are more likely than others, that the tunnel is open more often than closed. 90% of the time maybe it's open. But after you factor that in and you look at the likelihood ratio, it's basically a Bayes formula to decide which has the highest posterior. That's if there was no connection between the state of the tunnel today and tomorrow. The difficulty comes in from the fact that there is a connection between the two. So what would you do with the following sequence? 9, 12, 9, 8, 7, 25, 9, 10, 9. Okay? If you were to judge each day by itself, then you would say open, 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 probably closed, open, open, open. But now you know that the states of the tunnel are not determined every day independently, but there are projects, and projects take time, and it's very unlikely that the project took exactly one day. So now you're tempted to think that maybe this is not closed, this is also open. Maybe. I mean, if this seems too extreme to you, I'll bring it down to 18. At some point, you will be influenced by the fact that you're in the middle of a long chain of being open. And I can give you an example in the other direction. When it's closed for a long time, and it's highly unlikely that it'll open just for one day. So the problem of predicting the state from the arrival time is complicated by the fact that you're not considering only the observable, the arrival time, but also you have to consider the possible value of the state of the tunnel the day before and the day after. Okay, so the one problem we discussed so far that your friend may have to do is that you will have to do is, given a set of observations, deduce the most likely underlying state sequence. A related problem is, instead of the most likely underlying state sequence, maybe compute a posterior over the state sequences. Like every possible state sequence, what is the probability of that? And then the most likely one is just taking the maximum of the posterior. The second problem you might face is actually needed in order to solve the first problem, and that is, how do you learn the parameters in the first place? How do you learn these probabilities and these Gaussians just from a large number of observables? And I've already mentioned that what complicates things is that you don't know where to assign every data point, every arrival time. You don't know what color to put it into. So this is a hidden Markov model, and these are the problems associated with hidden Markov models. And it turns out there are solutions to these problems. Not perfect solutions, but decent solutions, which make hidden Markov models very, very powerful and very useful in many areas where you have a natural sequence, often time sequence, not always, but often time sequence. And there are also generalizations of hidden Markov models along different dimensions. For example, the time here is discrete, days. You can generalize it to continuous time Markov models. The state space here is discrete. You only have 3 states. You can think of having 1,000 states, but you can also think of a continuum of states. You can think of states being embedded in like a 2-dimensional, these are called Kalman filters. And there are several other generalizations, higher order Markov models, factorial Markov models. But the very simple vanilla Markov model with discrete finite number of states and either discrete or continuous emission probabilities is extremely useful, and in fact is at the heart of a lot of AI today. Speech recognition didn't get anywhere until sometime in the late 70s. People started using hidden Markov models, and then all of a sudden had a breakthrough. And now all modern speech recognition is based on hidden Markov models. Vision, a large amount of vision is based on hidden Markov models, although in vision it's now no longer a single sequence. I mean, in speech you can think about it as a time sequence. In vision you have the 2-dimensional aspect, so you may need generalizations that push you more in the direction of Bayes nets, because as I mentioned to you, hidden Markov models are a form of Bayes net. Okay, I wanted to give you just the overview and the intuition. Now I'll go with you through the sort of the notation and the more details. But really everything you need at some level, the high level, we already covered. I'll try to use the notation that is used, and this is, by the way, is not in the book. It's a separate standalone lecture. However, the slides are up, and you will definitely need them for your assignment, which would be to actually program a hidden Markov model learning and to use it. So first, there are Markov models, not hidden. And here the example consists of 2 states. We'll call them A and B instead of our 3 states. Here are the transition probabilities. You should familiarize yourself with the notation and the letters that are used for it. So S stands for state. State I, state J correspond to A or B, or in our case, open, closed, and semi-open. Q is a random variable that holds on the value of the state that the system is in at time t. So Q sub t will hold as a value either S1 or S2, in our case close, open, semi-open. So the S's are not random variables, they're just names of the states. State 1, state 2, all the way through state n. The Q's are random variables. We don't know what their value is, and they have some distribution of values. These are the hidden states. Then the first order Markov assumption, if you remember, is the one that says that the state of the tunnel, the state of the system at time t depends only on its state at time t minus 1. And the way they write it here is the probability that the state of the system at time t is Si, conditioned on the fact that the state of the system at time t minus 1 is Sj, and at time t minus 2 is Sk, and at time t minus 3 is something else, and so forth, is the same as the state of the system at time t being Si, conditioned only on the state of the system at time t minus 1 being Sj. So basically they took everything up to here and crossed out this thing. So that's a way of saying that the state depends only on the last state and not on anything before it. And because that's the case, it can be characterized by a single number, AJI, probability of transitioning from I to J, and captured by what we call the transition matrix A, which is an n by n matrix. So big A is the whole matrix, small a is an individual value in the matrix. Now, in a hidden Markov model, I described the regular Markov model to you as having also the emissions, which is fine, but you can think about it as irrelevant, the emissions. If you know, in a regular non-hidden Markov model, you know the state of the system at any time, there really are no problems. It's a straightforward, there are no estimation problem, there's no inference problem. The distinction between the emissions, the arrival times, and the state of the system becomes important if the state of the system is hidden. So, elements of a hidden Markov model, you have a set of states from S0 to Sn, so actually n plus 1 states here. We didn't talk about what state the system starts in. You know, if you have a whole sequence of arrival times, do you make some assumption about what state the tunnel was in the day before the sequence started? Typically, the way we solve it, there are two ways to solve it. One is to assume some stationary distribution, assume that before you started there's a 90% chance that it was open and a 5% chance it was closed and 5% semi. Or we can assume some additional state, which here is called S sub 0, which is an initial state, which doesn't have necessarily any physical realization. It doesn't correspond to anything. It's just a state from which you move to the other states, and you nonetheless need to specify a transition probability on moving from it to any other states. It's just a notation. It's not something very deep. It's called S0 here, and sometimes you may want to impose the condition that when the entire sequence is observed, at the very end the system would be in a final state. You may or may not want to impose that. In the case of a tunnel, there's no need, and it doesn't make any sense to insist that at the end the system is in final state. But there are some other processes you might want to model that you know you start from one condition and end up in another. Let's say you're modeling the melting of an ice cube, and you know that when you start all the molecules are frozen, and when you end all the molecules are liquid. But in between you don't know how many, and each number of molecules that's frozen is a different hidden state. So you know that there's going to be some kind of a transition, or maybe this is not, I need to work out this example a little more, but there may be some path of, many different paths of melting that ice cube, but at the end, you know, the final result is guaranteed to be a particular state. So we typically use S0 for an initial state and Sn for a final state if we choose to use one. Here we have the familiar state transition probabilities, and what we have in addition is the emission probabilities, which are here called output probabilities. And they're defined as the probability that given that at time t the system is in state J, the observable of time t, which is called yt, is some symbol taken from a finite alphabet of symbols. So here the observable is the y's, the random variable is the y's, and the values it can take are the o's O1 through OM, and they're described here as histograms. So you have two different histograms, and as you can see, these histograms are, well, you don't see the x-axis, but assuming it's the same x-axis, they can be overlapping. And that's where the difficulty arises. Now, in cases where the observables are not overlapping, we don't have a problem. Because if they're not overlapping, you can deduce immediately from the observable what the current state of the system is. If when the tunnel was open, arrival time varied between 9 minutes and 12 minutes, and when the tunnel was closed, arrival times varied from 35 to 45, and semi-open was 20 to 25, and if you knew for a fact that there's no overlap, then from the arrival times you can deduce directly the hidden state. Usually that's not the case. Usually there's overlap. That's where the problem starts. Sorry? The kind of overlap? It's an overlap between the possible values of the observables between the distributions based on different states. So overlap in the possible travel times between tunnel being open, being closed, and being semi. Okay, the hidden Markov assumptions, I mentioned one explicitly, the other one only implicitly. This is the explicit one. This is the one that says that the state of the system at time I depends only on its state at time j. The second one is that the observable at time t depends only on the state of the system at time t. I implied it, but I didn't say it. So you can certainly imagine a world in which travel time through the tunnel depends not only on whether the tunnel is open today, but also on whether it was open yesterday. Maybe the traffic jam was so bad that it lasted all night. I don't know. I mean, there are some situations where indeed this assumption may not be the right one, but nonetheless it's an important assumption in hidden Markov models. The observable of time t depends only on the state of the system at time t, and not on the state of the system at any other time or on the observable at any other time. Depends directly on any of those. Indirectly, of course, there is a relationship, as we saw here. So these are two Markov model assumptions. And now I want to present to you the three hidden Markov model problems. I talked to you only about two, and that is because I believe that only two have a really meaningful importance to you, but it turns out the third one has to be solved before as a sub-solution, as a step towards solving the other two. The two problems that I described to you, and let's start with those, are the decoding problems and the learning problem. The decoding problem is the one when I told you, suppose somebody gave you the model, complete with its parameters, so you know the emission probabilities and transition probabilities, and now they give you a new sequence of observables, and you are asked to guess what the underlying state sequence was for these observables. And I mentioned that you cannot be sure, but you may want to give the highest likelihood, the highest posterior guess. Okay? This is called the decoding problem, because you're decoding the underlying hidden state sequence from the surface observations. And you assume to have the model, to know the model. The model is based on data that was collected before. Assume that the situation can arise if you were on speaking term with your friends, and you collected all the data together, and you build the model together, you estimated the Gaussians together, you estimated transition probabilities together, and then he stopped talking to you. So now you have the model, but now you have a new week when he doesn't tell you what the state of the tunnel is in that week, and it's left to you to decode the state of the tunnel any one day in this week based on the arrival times. Okay? That's called the decoding problem, and the formulation here is, given an observation sequence, big O, which consists of all the little O's, and, it doesn't say here, and given the model, given the full specification of the model, find the state sequence, the hidden state sequence, that maximizes this posterior. I have to tell you what lambda is. So lambda is a shorthand for both the transition probability matrix and the emission probability values. So we said that the transitions are the A's. It's a n by n matrix, and the emission is J arrays of probabilities, and you can describe it, say, by a matrix B. So if you take A and B together and you call it lambda, this is your model. This is your full HMM. So I'm now living in a world where your model is given. Either your friend gave it to you or you had enough data to estimate it. You know the model. You know the full stochastic characterization of how the system behaves, how states follow other states, and how travel times follow from the state. So given a new observation sequence O and the old model, find the value of the hidden state sequence Q that maximizes this likelihood. Or similarly, it could maximize P of Q given lambda and O. Okay, it's the same thing because O is fixed. That's called the decoding problem. The second problem we talked about is the learning problem. Now let's say you broke relations with your office mate before the data was collected, so you don't have access to lambda, A or B. You only have access to a year's worth of arrival times. Can you come up with the lambda? Can you come up with emission and transition probabilities? They're not going to be the correct ones, but can you come up with a decent estimate? Maybe a maximum likelihood estimate. So the learning problem is, given an ensemble of observation sequences, adjust lambda so as to maximize the probability of all the observations that you saw given lambda. So this is the definition of a maximum likelihood estimate. Derive a maximum likelihood estimate for a hidden macro model from observables only. The first problem we haven't discussed yet is just an intermediate calculation that we need on the way to solving these two problems. It's called the evaluation problem. It's very similar to the decoding problem. It's a situation where you have the model, you're given the model, and you're given an observation sequence, just like in the decoding problem. But instead of calculating the most likely hidden state sequence, you're just asked to compute the probability of the sequence according to the model. It's not easy to see why you would want to do it, except as an intermediate step towards solving the other two problems. So we're actually going to do it in the order it's on the board. We're going to look at the solution to this one, and then use a similar solution to this one, and then use both of them to solve this one. We'll start with the forward problem. Oh, I'm sorry, it's called the evaluation problem here. So this was the last problem I mentioned, the one that was the very top of the list. You're given the model, you're given a new observation sequence, and you're asked to calculate the probability of this observation sequence according to the model. How would you do that? Okay, suppose for that one particular week your office mate was talking to you again. So they gave you the underlying state sequence. So first you have a model. Given the model, so you know all the emission and transition probabilities. And let's say you know the initial state as 0. You assume that you start from some state as 0. And now you're given an observation sequence O1, O2 through O, big T. And you're asked to calculate the probability of O1 through OT given the model. If your friend agreed, your office mate agreed to give you the underlying state sequence, Q1, Q2, Qt, what would the answer be? What is the probability of this sequence if you know the Qs? You need to go through the hidden Markov model and go through everything that happened to it, to happen to the state of the system to generate this. So you started from state S0 and you transition into the state Q1, right? And to do that took probability A S0 Q1. Remember that A has two indices, I and J, the state you came from, the state you went to. So you came from state S0 and you went to state Q1. And then when the system was in state Q1, it emitted a symbol O1. That was done with a probability that depended on the emission probabilities. So that was a B indexed with what? B indexed with Q1, and here in parentheses O1. So it's the probability of emitting symbol O1 when you're in state Q1. And then the system transitioned from state Q1 to state Q2, which was done with a probability that depends on the transition probability matrix, specifically the value of A that is indexed by what? Q1 to Q2, right? Transitioning from Q1 to Q2. And then being in state Q2, it emitted the symbol O2. This was done with probability B indexed by Q2 of O2. And we're going to keep going with A and B until we get to the last transition, which is from A QT-1 to QT, and then being in state T and emitting, being in state Q sub T and emitting symbol O sub T. So we have a product of NAs and NBs. Yes, you're quite right. If we know the Qs, really what we're calculating here is O1 OT, Q1 QT. Thank you. Now that's not what we want. We want P of O1 OT given lambda. If we had the Qs, we could calculate this, maybe to help us. But we don't have the Qs. So what do we do? All the Qs. Remember the law of total probability? We have to sum over all possible state sequences. So we have to do something like this, but sum over all possible sequences, hidden sequences, Q1 through Q big T. And put this in here. Here it is. Just as I suggested, you can write this down as a summation over all possible state sequences. Big Q is a sequence of Qs of this expression, which is the one we wrote on the board. So it's a summation over all possible values of the sequence of the product of A, B, A, B, A, B, all the way. Is this correct? Please.
Yes, but you could represent it much more succinctly because of independence assumptions.
Okay, but you're agreeing it is correct. Is this correct? Does anybody else see any problem with it? You got a problem with it?
You have to multiply that by the probability of getting it.
The probability of
each state sequence.
each state sequence. Well, I don't think so, because you already have the A's in here. So there's another way we can break down. Ooh, we're way over time. All right, I guess somebody is coming. We'll need to stop. Are we over time? No. Oh, sorry. Oh yeah, sorry. I thought this. All right, we have 5 minutes. There's another way you can break it down. You can write all the A's first. A S0 Q1, A Q1 Q2 through A Q T minus 1 QT, and then write all the B's. B of Q0, of Q1 O1 all the way through B of QT OT. And what this allows you to do is write it as P of Q conditioned on the model, and this is P of O given Q in the model. Okay? So this hopefully answers your question in terms of this is P of O given the model, can be written as sum over all possible Q's of P of Q given the model times P of O given Q in the model. We're summing over the unknown. This is a very common thing we do in probability estimation. I'll write it again here in a slightly different form. First, I can drop the dependence on the model, because everything depends on the model here. So just for convenience and for easier for you to see, I will just throw away the dependence on the model. But remember that everything is given the model. So I'm looking for P of O. Remember that O is an array. And I'm writing it down as a sum over all possible unknown values of P of O and Q. This part is clear, right? You sum over the sum part, you get the marginal. And now I'm going to further write it as a chain rule. First P of Q, and then P of O given Q. That's what I did here. And if you now introduce the model here and everything, the model is always in the background, something to condition on. Okay, so this is completely legal and completely correct mathematically, but it has one problem. Somebody else? What's the problem? It's not realistic. What do you mean by that? The number of paths we're going to sum over is exponential. Exponential in the length of the path, t. So we could do that. But to do that explicitly would mean to sum over an exponential number of these products. So making any one of these products is and multiplying n times, 2n times. It's not a big deal. But there are many, many such products of 2n terms that all have to be summed together. And it goes very, very fast, exponentially, so we can't afford to do that. But as was pointed out, remind me of your name? Isaac. As Isaac pointed out, there is a more efficient way of doing that. And the more efficient way of doing that will take advantage of the Markov property. This is exactly where the Markov property comes in. The fact that what happens at any one time doesn't depend on anything else in the world except where we were the time before that. So we're going to use an algorithm that is a form of dynamic programming. I don't know if you guys are familiar with dynamic programming. If not, it's a good introduction to dynamic programming. Dynamic programming is a general family of algorithms that allows you to calculate implicitly over an exponential number of paths using only a polynomial amount of computation. And I know now that we don't have time for that. But what I do encourage you to do, not encourage, require, go to the slides and read them over and be prepared, because this is pretty hairy math what's coming up soon, especially the learning part. And it'll be very hard to absorb it all just from one lecture. So read it ahead of time, come prepared, you will get a lot more out of it. Thank you.